Today we are working with continuity and one-sided limits. To say that a function is continuous at a point C, it has to be unbroken, it can't have any holes, jumps, or gaps. So I have drawn three different situations, all of them from an interval A to B, and the first example, we're always going to have a point C in the middle, and here our function is not defined at point C, there's a hole. So it's not continuous at C. In our second situation, we have a solid dot here, so we are defined at C, but the limit as x approaches C does not exist because we don't connect from the left and the right side. And in our last situation, we have a hole at C, but we're still defined there somewhere else. In this case, our limit as x approaches C of our function is not equal to the function value at C. So any of these three situations cause a function that is not continuous at point C. To have continuity at a point, we have to meet the following conditions. So pretty much offset what we did up above. We have to be defined at that point C. The limit as x approaches C of our function has to exist, and the limit as x approaches C of our function has to be equal to the function value. So that offsets all three of our situations up above. There's a couple different kinds of discontinuity at a point C. First, we have a removable discontinuity. We're going to have two situations this time, both from A to B. The first situation looks very similar to our first one. And the second situation is the third one, where we have a point elsewhere. So these are both called removable discontinuities because they only occur at one point. So you could plug in a dot on that point and then it would be removable. The discontinuity would be removed. A non-removable discontinuity, however, looks more like our second situation where it's at a point, but there's a huge hole, a huge gap, and it can't just be filled by one point. So an asymptote would be a non-removable discontinuity, for example. Okay, now we're going to do some specific examples. The function 1 over x looks like this. Obviously, if we plug 0 into this function, we would be given an asymptote because it would be undefined. So we are continuous on all reals of this function except for at 0, and it is non-removable. It's not just one point, it is a huge gap. Any asymptote is a non-removable discontinuity. Okay, at B, our function looks like a line, but if you look super close, you see a hole at x equals 1. So that means that we are continuous again on all reals except for at one point. This time it's 1. And because it's just at a point, and if we had a function value there, we could fill in that discontinuity. That means that we are a removable discontinuity. Okay, C is a piecewise function. It is the line x plus 1 when x is less than or equal to 0. So that's right here. And x squared plus 1 when x is greater than 0, which means it looks like that. And they do meet at this point, and since we are including 0 on the upper half of the piecewise function, that means that 0 does not have a hole there. And because they meet up, we can say that it is continuous on all reals. No holes. and the sine function. Like this. Obviously, it's not going to have any holes or anything because it's a normal sine function, so this one is also continuous on all rails. Okay, now we're going to talk about left and right-handed limits. As we talked about before, in order for a limit to exist, it has to approach the same thing from both sides. In this case, we're just looking at right-handed or left-handed limits. The plus sign means right-handed, and the minus sign means left-handed, and you are going to find it the same way. Only you're not going to look at both directions, you're just going to look at one direction. Okay, we want to find the limit of square root of 4 minus x squared as it approaches negative 2 from the right. So let's just look at what this function is. It's a semicircle, so let me do my best here. If we are approaching negative 2 from the right, here's negative 2. As we approach it from the right, we are approaching the y value of 0. So our limit as x approaches negative 2 from the right of our function is 0. Greatest integer function, we can find this on our calculators under math number, that's number 5, int, to graph. So obviously at every integer that it changes. Okay, I think that's all we need. Looks something like that. We are trying to find the limit at 0 from both directions. Okay, so first let's do the left-handed limit. We are trying to approach 0 from the left. Now we have to be on this step. And we are approaching negative 1. We're on the negative 1 y value that whole time. Coming from the right, however, we have to start at this one, coming at 0, and we're at 0 the whole time. Okay, so for the greatest integer function, you just need to figure out which step you're on. Okay, in order for a limit to exist, we talked about this with the definition of a basic limit, the left-handed limit has to be equal to L and the right-handed limit has to be equal to L in order for the limit to exist. To be continuous on a closed interval, you have to be continuous on the open interval, and your right-handed limit of the first point in your interval needs to be equal to the function value, and the left-handed limit coming from the right endpoint has to be equal to the function value as well. It's a very confusing definition, so we're going to go ahead and do an example of that to prove that we are continuous on a closed interval. This function, square root of 1 minus x squared, looks like that. It's also a semicircle. So we are looking at the whole domain here. It's negative 1 to 1. Now we are trying to prove that it's continuous on that whole domain. First we need to show that it's continuous on the open interval from negative 1 to 1, which it is. Just looking at it we can tell that it is. If you need to look on your graphing calculator at the table, you can certainly do that to prove it to yourself, but it is. Next we are trying to prove that the right-handed limit going at the left endpoint is equal to the function value at the right endpoint. And as you can see, the right-handed limit of negative 1 is 0, which is also the function value, so that's good news. And we then need to show that the left-handed limit of the right endpoint is equal to the function value of that endpoint. And from the left, we are approaching 0 again, which is the function value of 1. So there's 3 things you need to show. Continuity on the open, both limits, then you can say that it's continuous on the closed. And you're done. Okay, here's some properties of continuity. If we have a scalar multiple b, and we have two functions f and g, and they are both continuous at a point c, then the scalar multiple is also continuous at c. You can add or subtract the two functions and it's still going to be continuous. You can multiply the two functions and it's still going to be continuous. And you can divide as long as the bottom is not going to give you a 0. Okay, so if g is continuous at a point c and f is continuous at g of c, then the composite function given by f of g of x is continuous at c. That tells us that the limit as x approaches c of f of g of x is in fact f of g of c. Again, just plugging in the c value, which is what we've been doing so far with limits. Okay, describe the interval on which each function is continuous. Tangent function. This is what the tangent function looks like. This goes from negative pi over 2 to positive pi over 2. So we can say that it's continuous from negative pi over 2 to pi over 2, and then we are adding n pi because it repeats every pi. That's what the period of the tangent function is. Okay, the next one. Sine of 1 over x and 0. Okay, so this one looks really crazy as we're approaching 0. But it's telling us that because this is a piecewise function, we also have a point 0, 0. But sine of 1 over x never actually gets to 0, 0. So is this actually continuous on everything? No, it's continuous everywhere except for 0. So if we want to give an interval of continuity, it's continuous from negative infinity to 0 and from 0 to infinity, not including 0. We're actually going to skip part C. Last thing we're going to talk about is the intermediate value theorem. If we have a function that's continuous on a closed interval from a to b, and there's a value k that's in between f of a and f of b, that means there's at least one number c in our interval where f of c is equal to k. Now let me just show you what that means. Closed interval from a to b. Here's f of a. Here's f of b. Doesn't really matter what's going on in between. This function, this theorem is saying that there's some value k in between there somewhere, in between f of a and f of b, such that there's going to be a c value where f of c is equal to k. This is just proving that there's an existence of that point. We're not actually showing what the point is or proving what the point is. We're just proving that there is a point there. Okay, now I'm going to show you how to use the intermediate value theorem. Now, if you're going to take the AP Calculus test, this is something that is definitely going to come up, so paying close attention or understanding this concept is important. We're trying to show that there's a 0 between 0 and 1 of our function x cubed plus 2x minus 1 on that interval. This is what our function looks like. So obviously we can see that there's a 0 there. But we can't just say, well, I see it, so we're good. First thing we need to show is that it's continuous on the closed, which it is. We need to know what the endpoints are. The endpoint for 0 is -1. The endpoint for 1 is 2. So because between -1 and 2 there's definitely a 0 by the intermediate value theorem, there has to be c value in our interval from 0 to 1. Such that f of c is equal to 0. And that is really that easy. You just need to know when to use it and how to use it. All right, that was our section on continuity.